soon we will. Okay, so now it's 4:15, and we are ready to get started for today's lecture. Okay, so what will happen today is that we're going to close the discussion about equation of motion, and then I'm going to explain. I said last week that I'm not going to introduce any additional information to what we already learned in the first 6 weeks, but as usually, I'm kind of bending the rules a little bit, and this time I'm bending the rules a little bit because I will introduce you a short subject matter that is called Constraint Stoppablization. That for sure will be the last item that is needed in written exam. And again, remember, written exam will be on next week, an entire week, starting from Monday morning at 0:05 all the way to Sunday evening 23:55. So right 5 minutes past the midnight it will be on, and 5 minutes before the midnight it will be closed. So today definitely most of the part is devoted to this thing. So this is this summary, kind of like what is the important thing from all these subject matter that we have learned, and I try to make your life as easy as possible. And the one of the ways that I want to make your life as easy as possible is that I'm going to create each one of the subject matters by number of stars. So if there's a lot of stars, this is what I'm definitely expecting you to master prior to exam. It also serves another purpose, because I know that you guys are very busy and you have a million things in your plate. Maybe you need to prioritize. Maybe you don't have enough time to cover all this material that we've been discussed, but some of them. But which one of them makes sense to study in details? Those are the one with the highest possible number of stars. So it helps you also to kind of focus on the important subject matters and leaving rest with, not necessarily with no attention, but less attention. Okay, so that's what's going to happen today. And I see that we still have amazingly low number of participants. We only have 63 participants. I have no idea why it is this low, but remember, if you're unable to follow the streaming, make sure that you're following the recording there. And the recording will be, of course, available in YouTube site. Okay, last week we discussed quite a bit about how is that we can express the equation of motion. And we concluded that for the constraint system, when we are expressing the concept of virtual work, the virtual work for constraint system cannot be set to be equal to 0. And this, by the way, is the most often used misconcept of virtual work. People consider the virtual work that no matter what you do with the virtual work, you can always set that to be equal to 0. No, you cannot. You can only set this to be equal to 0 if this virtual displacement is kinematically admissible. And I got the information that there is something not so clear today. I have an information that there's an excellent connection in my end. So maybe something in your screen. What about others? Is this okay? So they say that the picture is blurred. No comments. Okay, so others are saying it's okay. Others are saying that it is okay. It's just that maybe it's that end, or maybe again my internet connection, which is this guy here, is not willing to cooperate. I think it is not my end, because here I have a green light, an excellent connection. Okay, thank you. All right, so yeah, I was about to explain that virtual work, in the concept of virtual work, you can set the virtual work to be equal to 0 only if this virtual displacement is kinematically admissible, meaning that it obeys the constraint, is not violating against the constraints. Okay, how it is expressed here will definitely violate against the constraints. And why is that? That's simply because the virtual displacement is imposed to all the generalized coordinates. So it's meaning that you rotating and translating all the bodies regardless of the joints. For sure you cannot violate against the constraints, and when that's the case, then you cannot set this equation to be equal to 0. So we have to do something in this regard. We have basically two ways to solve this problem. We can either substitute the constraints inside of the equation, which will be one possibility, or we can add the constraints to the original equation with help of Lagrange multipliers. And that's exactly what we are following here. And this is called augmented formulation. Augmented formulation, we adding constraints to original equation. So how that works? It works this way, that we adding the constraints to original equation, and that will be carried out with help of Jacobian Matrix and Lagrange multipliers. Now, if I have a system, let's say that I have a pendulum system like this. In a pendulum system, I need to use two constraint equations to be able to express this revolution. Two constraint equations. It means that there will be two Lagrange multipliers in the system, which is a pendulum system. These two Lagrange multipliers will have a physical interpretation, and its reaction forces due to the constraints. These reaction forces will be the force this direction and force this direction. Those will be my reaction forces due to the constraints. Okay, so now I'm able to set this equation to be equal to 0. Okay, so that's almost end of the story. Almost. Except that I also need to use constraints to make sure that I have enough information versus the number of unknowns. Because as equation, I think I need to take a little bit of stuff off here to make it this more readable. Now, here. And we'll take this drawing off. Okay, like this. So if I'm just going to look at this equation, this is not enough information me to solve the problem. Why is that? Because my unknowns are this one here, acceleration of generalized coordinates. And if I'm dealing with the one body, this, let's go back to this pendulum case here. In the case of pendulum body, every body needs 3 generalized coordinates, meaning that this vector here will consist of 3 components. Okay, so those are my unknowns. So I have 3 equations, 3 unknowns, but this guy here, that 2 is an unknown. So that's not enough information for me to solve the problem, because this is this vector of Lagrange multipliers is a vector of 2 components, reaction forces. So in total, in a pendulum system, I have 5 unknowns. 3 of them are associated generalized coordinates, and 2 of them are associated to reaction forces due to the constraints. Okay, so this is my set of equation of motion. I could use that as it is, but it's a little difficult to use because time integration schemes are not easy to implement to a set of differential algebraic equations. So this is called differential algebraic equations. So final thing that I'm doing, the final step that I'm doing, I'm converting my set of differential algebraic equation to be ordinary differential equation. So how it reads after that, it's going to be this one here. So this is my equation of motion. And when you look at that in a bigger font, that's it. This is what I'm solving. And my unknowns here, let me repeat. My unknowns, because I'm going to ask that in a second. My unknowns are here, acceleration of generalized coordinates and Lagrange multipliers. And the components that I have here is, of course, mass matrix, Jacobian matrix with transpose operation, externally applied generalized forces, quadratic velocity vector, which often is equal to 0, particularly in planar cases, and the guy that have no name. The guy that have no name is a constraint differentiated twice with respect to constraint. Okay, so that's what we look. And last week we were able to apply this procedure to simple pendulum structure. Not the pendulum, but system with the one moving body. And this one moving body is constrained to ground by a primitive joint here in a point P, a primitive joint here in a point Q. So this point here, point P, can slide along the global y-axis, and the point Q can slide along the global x-axis. And we made quite a bit of work. Eventually, we were able to solve it, and the equation of motion finally looked like this. And look at this. So this is exactly this equation, with the exception, of course, that this one here, which is called system matrix, was moved to the right-hand side of the equation and inverted, because otherwise you cannot move it to that right-hand side of the equation. So this is how it looks. So this is what you need to invert. You need to actually invert that in every time step. And then you're able to solve your acceleration and Lagrange multipliers. And then you're using time integration scheme to solve velocity from the acceleration and then position from velocities. And that's how the procedure actually works. And this is called solving the dynamics. Now, this is where we stopped last week. I still have a little bit of additional stuff, but already this time what I will do is that I will show you how is a first in class quiz. And the first in class quiz is this. In the augmented formulation, unknowns are, and again, the augmented formulation is this one here in the case of a pendulum, and in the general case, this one here. Now, I'm asking here, in the augmented formulation, unknowns are the ones that I'm solving is an acceleration of generalized coordinates, Lagrange multipliers, generalized forces, acceleration of generalized coordinates, and Lagrange multipliers. I know that there's a deja vu. And yeah, I want to ask this again. So we discussed this last week, but I would like to ask this again. So please place your answers to Socrates. And meanwhile, I will show you something amazing, something that you don't believe in your eyes. So because what I will do is this. So I will solve the response of this pendulum structure, and I will solve the response by using a MATLAB. So now I just need to figure out where is that my mouse is traveling. So it's here. So it's a bit, let me see if I can make this a bit smaller. No, this is standard size. It's a little difficult to change this. So I have here my model. So I have 3 generalized coordinates. So I have position and velocity level for coordinate 1, which is rx. Then the same for ry, and then the same for angle theta. And then I'm expressing, well, these are the little bit further information. I'm giving the initial values, which is a mass, gravity constant, length of the body, initial angle, which is computed as it is shown here, and constraints and other information is provided in other file, which we're going to take a look at in a minute. This is my initial condition, and then I'm providing the mass matrix, and then I'm just running solving this in forward of time. And let me show it to you how is a model itself. This is my model, and what I have here is a Jacobian matrix, another component. So this is how the Jacobian matrix, I'm sorry, this is not the right file. This is the right file. So this is my Jacobian matrix, exactly the one we look in that numerical example. And then my external applied forces is here, which is just a gravity force. So it's a mass multiplied by gravity constant. Quadratic velocity vector is equal to 0. So we don't need to worry about that. And this is the vector QC here. So the implementation is completed. So let's see what happens when I'm solving this. Ready? Oh my God, what is this? Am I in the wrong place? Here. Now. Okay. Ready? Oh, I need to take this here to make this more visible. I hope that it's still, yeah, it's still visible. Ready? Because this is the highlight of your life. not necessarily life, but at least a highlight of this course so far. Remember, we did similar kind of mechanism, but in a kinematics. And now we're going to solve the dynamics of same kind of kinematics. And here it is. Here it is. Look at this. Oh my God, unbelievable. This is unbelievable. So we made it. So we were able to solve this mechanism using this multi-body approach. And of course, we are able to produce the information about all possible quantities that we computed, including reaction forces. So here's my reaction forces. Here's reaction forces in another direction. This is rotation of the local coordinate system. This is a position of local coordinate system in global x-axis, y-axis, so on and so forth. So I'm able to do it. Okay, I know that this is not too impressive, so you may wonder, like, seriously? So I spent, what is it, like several weeks in my life, and we ended up to have this simple pendulum. Yes, it was a simple pendulum, but more important than the simple pendulum is that we have this procedure that consists of 6 steps. This 6 steps, and once you follow in the 6 steps, you get the equation of motion automatically. No thinking needed. No need to find any kind of relation between, some weird components. You're just following the steps. You have the equation of motion. You are saying to whatever software you wanted to use that, please go ahead and solve this to me in forward of time, and that's it. So that is a beauty of multi-body system dynamics. So it's very straightforward, very simple to use if you follow these steps, these 6 steps. With that, I would like to take a look how is the first in-class quiz of today. Hold on, now I'm not sure where is my, I think it's here. I think I found it. Yeah, here. So I have 79 students, and out of the 79 students, 75 already entered the answer. And I see that the lottery is going on, so the game is on again. Okay. My personal guess, what is the success rate today? Today's success rate is 82. 82. Yes. 82. It's quite low, but it's low because, I'm pretty sure that your reasoning goes such that no need to invest to these scores yet. And no need to invest in this course yet because the exam is next week. So why bother to do it this time? But definitely it makes sense if you invested some serious effort, working effort to this course this time. It will pay off. Now it's kind of still waiting the last student to enter the answer. Let's see. I think that I will close this game and we will take a look. How is it? Okay, so we have several guesses. How is the success rate? Oh yeah, now we have all the students entered the answer, and the success rate is 95. 95 is a very good number. It's a very good number. Of course, it will be. The one thing that bothers me a little bit is that there is one answer which says that generalized forces are unknowns. For sure, they are not unknowns because the forces are the ones that we do know, and then we wanted to solve the response. So it's like this Newton's second law. I don't know where can I write there. I think I need to clear a little bit my screen. This one here. So it's like external applied force. This is the force, and this is my inertial forces. So you know this, for sure you know this. This is something that you take and you solving the response by solving first this one and then using the time integration scheme. So I'm checking I'm checking how is the chat, and somebody already checked that there's no right guesses. Too bad. Okay, but already this time, listen to me. I have some good news to you. End of the day, I have a classical in-class quiz, and guess what? I'm gonna ask, how is that you can describe the rotation of particle? I will ask that. Okay, how you can describe the rotational particle? One option is that you don't describe the rotational particle because it makes no sense. That is, of course, the correct answer. Then there's a bunch of nonsense. None of these nonsense makes any sense. Make sure that you do understand that the particle rotation is something that is non-existing. So as soon as somebody started to explain about how is a particle rotation, you said, stop right there, because that makes no sense. Okay, so that will be later today. That will be the end of the day. One more in-class quiz. There is actually plenty of in-class quizzes today. And the last one, if I remember correctly, if not the last one, then the second last one is about how is a particle rotation. Okay, somebody already loved the particle rotation. It is a really difficult thing, and there's a high temptation in my side to put the question like that in the written exam as well. Okay, so now the final topic is this constraint stabilization. And prior to that, let's look at one more example. And this example nicely takes us to the topic of constraint stabilization. So now I'm going to revisit the example that we studied. I think this was 2 weeks back, 3 weeks back, something like that. So we look at the simple mechanism that consists of two bodies. And 2 weeks ago, 3 weeks ago roughly, we introduced a motion constraint to this point Q. And we said that the point Q cannot move freely, but it has to follow the certain pre-described motion. Okay, that's what we did. Today we're going to do this example, but a different way. This time we have constraints such that there is a revolute joint here, revolute joint here, and primitive joint here. That means that there is a total of 5 constraint equations, because 2 revolute joints, so it's going to give you 4 plus 1 primitive joint. So there's a 5 constraint equations. 5 constraint equations. How many generalized coordinates we have in this system? Remember, everybody needs 3 generalized coordinates. Okay, how many bodies we have here? Well, we have here 2. 1, 2. How many generalized coordinates? That's going to be obviously 2 multiplied by 3, which is 6. Okay, so that we have 6 minus 5 degrees of freedom, meaning we have 1 degree of freedom in the system. 1 degree of freedom, meaning that the system can move one way only. But because the system have 1 degree of freedom, this is not solvable by using kinematics, but we have to use dynamics to solve the response. We actually have some forces in both the systems. So we have gravity force here, so it's a little bit of small fun, but there's a gravity force here. And we're simply going to study how is that the system will perform under the gravity. So that's how it goes. So there, I see that there is some comments going on. So this obviously this particle rotation is something that makes people to I don't know, they raise a little bit of discussion. I will get back to this discussion a bit later. But first, what I will do is that I will close this example. Okay, now here is one more in-class quiz. This system we'll look at. What is a number of unknowns? How many unknowns we have to solve here? And the choices are 2, because of 2 bodies. 6, because of 6 generalized coordinates. 11, because generalized coordinates plus constraint equations. I mean, generalized coordinate plus Lagrange multipliers. And 14, higher the better. So those are the choices. And hold on, so my Socrative is not on yet. So let me put it on so it's visible right now. It's kind of weird that I can see that we have 83 students that are following the stream, but only 79 are active in Socrates. Well, anyways, so what is a correct number? What is the number of unknowns we have to solve here? And again, 2 because of the 2 bodies, 6 because of the 6 generalized coordinates, 11 because of the generalized coordinates plus constraint equations. Well, that's equal than the Lagrange multipliers, and 14 is like high number. And team here is our reasoning to select this would be higher the better. Okay, so I need to give you some time to think about this. So please think this is not, this is an application from the previous in-class quiz, so I'm sure you can do the math. And the game is on, so the first lottery answers or the lotteries are already in the chat window. My personal guess here is that success rate will be, how was it in the last time? I think it was a 95. My guess here is, look at this. So this is that high number. So this would be ridiculously close to 100%, but not 100%. Remember what is 100%. So if you're able to do the 100%, you can get several extra points. Each of you will get extra point because you're doing so well as a team. And then those of you that are guessing 100% will get the 1 additional point. But I see that the guesses are much lower than that, which is kind of confused because, so I don't know. So we'll see what it is, what is the correct answer. Then what we will do meanwhile is that we're going to follow these 6 steps to create the equation motion for this system with 2 moving bodies. This time, we're not going to use too much about sophisticated mathematics, but instead, we're going to simply use a pre-calculated tables. So from the pre-calculated tables, well, first of all, we can see that we are dealing with the beam-like bodies. And when we are dealing with the beam-like bodies, that the mass moment of inertia will be mass multiplied by length power 2 divided by 12. And because another important observation that body reference coordinate systems in both bodies are located in the center of the mass, it means that the mass matrix will have diagonal shape. Okay, so this is a diagonal shape, and this is a diagonal shape. So these are the mass matrices for the body A and body B. And now when we're constructing the system mass matrix, we're simply going to place these 2 matrices as it is shown here. Now again, no overlapping. So this one here have a dimension 6 by 6 because of the 6 generalized coordinates. Okay, now there seems to be a little bit of difficulties that somebody is unable to log into Socrates. I'm going to wait until the end of this example, and then I will take a look how is a result of in-class quizzes. Okay, so that was step number 1. Step number 2, Jacobian matrix. First important thing we have to have in a Jacobian matrix are the constraints. Once we have the constraints, then you just use a mechanical mathematics and that's it. Okay, so the first constraint is the one that is located here. So this is point O. Point O is located in origin of the global coordinate system. So can we do this such the way that we're not going to make a visit in a body reference coordinate system, but we somehow make a shortcut and we stay here because we started here. So can we decide not to come here and then back? For sure not. You do something like that, that will be considered as a criminal action. Remember, always, no matter what you do, you're always traveling the body reference coordinate system and then whatever you want. Even sometimes you need to come back, but still you have to make via body reference coordinate system. How that will be made it happen? Well, that's going to be simple. So you take, first your vector R that takes you the body reference coordinate system, Then you are counting the orientation of body reference coordinate system, and vector u bar takes you whatever final destination you may have. And here, the x-axis is pointing this direction, so you have to travel minus L divided by 2 to reach this location. Now, this zeros here refers to the fact that this point that we wanted to constrain is actually located in the center of the body, the global coordinate system. So that's going to give you two constraint equations, 1 and 2, and that's it. Then the second one, again, I need to make this more readable. Oh my God, not that. I don't want to delete that. Okay. Okay, let's take this back. Now the second constraint is the one that is point P here. The point P is common in body A and body B. Okay, how we can make it happen? Again, we're going to use this equation, the only equation we know very well. So this equation is this one. So first translating ourselves to body reference coordinate system, then the rotation of the body reference coordinate system, and vector u bar. Okay, vector u bar for the first body is going to be L divided by 2. For the second body is going to be minus L divided by 2. Okay, that will give you two additional constraints. My final constraint is a primitive point that is associated to this point Q here, meaning that this point Q cannot travel along the global y-axis. That's not allowed. Meaning that once I describe this point here, I need to set this guy here, to be equal to 0. So it's going to be this one here, this multiplied by this one. That's going to be my fifth constraint equation. So now I have my constraint equations, and then ready to go and compute the Jacobian matrix. Jacobian matrix is nothing but the mechanical mathematics. You make your list of constraint equations and you differentiate those with respect to your generalized coordinates. How many generalized coordinates? Six generalized coordinates, because 2 moving bodies, every body needs 3 generalized coordinates. Okay. Then externally applied forces, that's going to be quite straightforward, and the reason being that we only have a gravity force, and the gravity force is applying in the center of the mass, and the body reference coordinate systems again are located in the center of the mass. So the mapping matrix will be in a very simple form. Okay, so how it looks. So gravity force, this is made it in a a little bit complicated way. So we are first going to take a look at where the force is applying in a body A, and I'm concluding that in that particular place the vector u bar is 0, 0 vector, because it's here and this is where the force is applying. What is left is this one here. Once I differentiated this vector with respect to my generalized coordinates, my mapping matrix will be simple like this. So once I do the math, once I multiply force expressed in global coordinate system with respect to my mapping matrix, this is how the forces look like in the first body case. In the second body case, well, I'm just going to redo the whole thing again. I'm going to look at how is this point here, and then differentiate that point with respect to generalized coordinates, and I will get the mapping matrix. This is how is my mapping matrix. And finally, oh yeah, I see that there is an additional force here. So there's a point force pointing right, positive x-axis. I was wondering where this is coming from. This is my point force, and this is my gravity force. External applied forces look like this. Now I'm ready to combine this information, and the combination goes such that these are the forces associated to body A, these are the forces associated to body B. Okay, quadratic velocity vector, don't need to bother to look at that because we have a diagonal mass matrix, so the quadratic velocity vector will be automatically equal to 0. So one more step to take. And one more step to take is this painful QC component. And the only thing that will be left here is this one here, which is Jacobian matrix multiplied by velocity of generalized coordinates. That's going to be a vector which will be differentiated with respect to generalized coordinates. Finally, that will be multiplied by velocity of generalized coordinates. Okay, so let's get started. Here is Jacobian matrix. Here is a velocity of generalized coordinates. Once I multiply, I do this multiplication matrix multiplied by vector, I will get the vector of 5 components. So 5 components. Once I differentiate that again with respect to generalized coordinates, I will get matrix. And once this matrix is finally multiplied with the vector velocity of generalized coordinates, I will get the vector of 5 components. That's it. Now the dimensions are becoming to be so large that I'm unable to put this in a one system matrix anymore, but that I can do in a MATLAB then. So MATLAB can do that for me. So let's take a look. How is the MATLAB capable to solve this? So I need to change the file a little bit. So let me show it to you. This, by the way, these files are available in Moodle database. So I have here my Jacobian matrix. So, it's just a one-to-one copy from my example. I'm sorry about that. And then my force vector is expressed here. This painful guy with the 5 components is expressed here. These are my external applied forces. And the one thing that I can see here is that I'm not consistent here, because look at this. My point force is missing in my implementation. Sorry about that. So if you wanted to add it, it's going to be here. This 0 should be the force component, the point force component pointing in the right. Okay, so this is how the system look like, and I think that I'm ready to solve the system. So let me move on to this file to see how it is. I think that everything is correct. No, not this one. Here, I don't want to use these. So these are my coordinates, and this is my mass matrix initial condition, and so on and so forth. I'm gonna change the error, so the error tolerance to be a little bit looser. I mean, not that as tight as it was in the beginning, and then I'm ready to go. Okay, so let's solve it. And here's my solution. Look at it, goes really fast solution. I think that I need to move this a little bit aside to make this visible for you. So let me visualize it for you. Okay, so it's flying like this. So it's flying like a bird a little bit. So that's how the crankshaft mechanism is obviously performing. So it's flying around and then it's moving like this. So, like if it is initially here, this is my revolute joint, this is the primitive joint, and started to do like this. Very nice. You're happy? You shouldn't be, because obviously this is incorrect solution. This makes no sense. Remember, I have constraint here in this end, and then I have primitive joint here, and obviously you see clearly here that I'm violating against the constraints big time, because this end, this one here should be here, not flying around like this. So come on, what happened here? So what happened for us was an integration error, because what I just did, just before I started to solving this problem, I lose the error tolerance to be quite high number, and obviously that number was not correct number. And that is something that we can only fix by using, well, there are kind of 2 ways to do it. We can use a primitive way to solve it, and the primitive way would be to using very tight error tolerance, or we can use constraint stabilization. Okay, so let's take a look. Let me go again and let me solve it. This with the tighter or smaller error tolerance and see if it makes any sense. Okay, so this is a new solution available. Okay, look at this. So now it's much better. So now it makes sense. Now it makes sense. Now the constraints are no longer violated, but again, there is a risk that if there is someone that is not knowing the business will select the incorrect error tolerances, and then the solution makes no sense. So we have to find bulletproof way to solve this problem, and the bulletproof way is this constraint stabilization. And now with that, I can see that I almost spent the first 45 minutes with this topic. I'm gonna take a look what's going on in the chat window, and then we're gonna look at how is a second in-class quiz. And okay, so okay, all right. I guess that there's not much I can learn from the in-class, these comments, but game is on. So what is your guess regarding the success rate of this guy? What is the number of unknowns? And this was again, this same problem we'll look at, how many unknowns I solved. The options are again 2, 6, 11, and 14. And those of you that have not yet answered, please do so we can close this game. How did I have this good vibe, some kind of weird good vibe in my body? So I'm thinking, could this be 100%? Could this be that? This, I think it maybe it's going to happen right now. I have never won in the lottery because, well, I don't do the lottery really, but I think this kind of feeling that people must have before they got the jackpot in the lottery. 100%. So 100%. Okay, so I can see that you guys are not as positive that I am, but okay, we'll see. Oh, you guesses are really, really way too low. I don't think it is 60, 56. That's 56 is way too low. My guess is 100%. 100%. And we have all the answers. And now okay, let's see if my vibe was correct. God damn it. Nowhere near to 100%. High. It's still high number. 75. Okay, maybe because I was explaining this in a little bit of misleading way, because I said that two bodies, making it kind of like temptation that you select option A. Two bodies has nothing to do with this problem, because basically what we need to look at how many generalized corners we have plus how many constraint equations we have. So 6 plus 5. So the correct solution is 11. 11. Okay, so now my last hope is this question about the rotation of particles. Remember, particles do not have rotation. No rotation. Particle, no rotation. Okay, and with that, let me do the following. Let me take these off. I'm going to shortly explain this constraint stabilization. I will be brief here. It's not going to be one of the core material in written exam. And then what follows after that is that we're going to move on to summary. Summary, I think it is more important than the stabilization this time. Okay, but you know that why the stabilization is needed. So it is needed because when we are integrating things in forward of time, we are introducing certain amount of errors. And now the thing we did when we converted to DIA, differential algebraic equations, to be ordinary differential equations, we actually did that in a way that we differentiated the constraint twice with respect to time. Excuse me. So in this equation of motion, constraints are accounted in acceleration only, because this is what actually lead us to this equation. Now, when we are coming back from the acceleration to velocity and then the position, every time we do it, we introduce a certain amount of errors. And errors tend to be accumulating. And when they are accumulating, long enough or large enough, then this equation that is very much enough where we started is no longer fulfilled. Because again, here from C dot dot, we are going to C dot. And from there, we're going to go to position. Each time I have an arrow here, I'm introducing integration errors. And this is something that we need to fix. This is a bit more mathematical explanation for that, because we are missing this constant, this integration constant. Those may be the ones that you remember from high school. I'm not going to take a look at that, but I'm instead going to look how is that we can fix this problem. So the problem which is coming from time integration scheme. So there's a little bit further information about where this accumulation problem is coming. Never mind about that. Now, here's my solution to the problem. I could consider to some tricks, and these tricks are something that I could use this acceleration level constraint, and then I can introduce some penalty factors, and these penalty factors, with help of the penalty factors, I'm able to take the constraints in the velocity and position level into account. So it's kind of considered, the best physical interpretation about this situation is that once we have a constraint, let's consider as a revolute joint, and we have a pendulum in a revolute joint. So then we're kind of introducing spring to both directions where the forces are enclosed and dampers. Sorry about the unclear writing, but there's a spring and a damper. So I want to make this kind of symbols here. The spring and dampers will make sure that if I'm trying to violate against the constraint, they're pushing the constraint back to where it's supposed to be, and not just pushing, but also damp it back. Because with the spring, it started to make all kind of vibration motion, but with the damper, it's not going to happen. So this is not what happens in real life, but in numerics. So in numerics, I have here damper and a spring, but my interpretation is coming from the real life. Okay, this is considered as a constraint stabilization. And once you have a constraint stabilization, then you do not violate against the constraint. That's it. Okay. That's it. I see that my timing is almost perfect. I can see that I have some connection problem here because, hold on, I see that my internet connection is no longer via my mobile phone, but it's something else. But it seems that there are no complaints. Just when I say that no complaints, there is quite a bit of complaints. Okay, so I should be back. Yeah, I know. For some reason, this guy again was not willing to cooperate with me. Okay, I should be back. So let me see how is my streaming today. So it's still saying that there's a little bit of problem. Let me relocate my phone. Okay, yeah, I think we'll still have an error message in my window, but it should be gone momentarily because right now the connection is via my mobile phone, and the mobile phone is located in a window of my basement office. So, okay. So the problem should disappear momentarily. I see that we're still struggling. I don't understand why it is still struggling, because it should be okay. Yeah, now it's again excellent connection, which is great because we're moving on to really the most important thing prior to written exam. Here's things that I would like you to know. And the list is how can I say it? Like, this is not looking good because that we are looking at the subject matters that are not easy. They are not easy. Look at this. Generalized inertia forces. This is very, very complicated thing. But I will give you a few hints how is that you can prepare yourself the written exam. And then I will show you a few examples how are the possible questions in written exam. But again, how it goes is that I have a question bank, and then I'm using the lottery to find the question for you. So when you think that I have an exactly same exam on Monday and Sunday, that's not the case. But there's a quite large question bank, and with lottery you get certain questions in your plate, and that's it. Now, let me see. Okay, so there's some instructions about how to use a YouTube. I'm not going to take a look at those in details. So I have here 3 slides, which I will take a look at in the very end of and I will explain in the very end of my presentation today. And these 3 slides are something that I would like to make a challenge, is to explain your multi-body system dynamics in 10 minutes. So all these lengthy, detailed explanation I wanted to summarize in 10 minutes. But before that, let's look at the different topics. And once we're done with the topics, then we're going to move back to these 3 slides. Now, here you see how I'm then rating, how is that I'm rating different subject matters. So these are all the matters that I'm expecting you to know. And each one of them are rated. So here's an example. Description of planar body is rated as a 5 stars. This is pretty much same than in a hotel stars. So if you have 5-star hotel, that's like best you can think of. This means that if there's one thing you need to know, it's going to be this one. So description of planar body. I'm expecting you to know this back and forth, no matter what, and no matter how is application. Okay, how is that the description of planar body? And again, you have to make a difference. What is a body and what is a particle? Let me explain again. Particle is an ingredient of body. A body consists of infinite number of particles. Particle is very, very small mathematical quantity. It's so small that its rotation makes no sense. It is so small. How is that we can describe all the particles that makes a body? Well, we decided to use or make that happen with help of the body reference coordinate system. Body reference coordinate system is like a system coordinate system that travels along with the body. All right. So I have here a potato-shaped body, and in my potato-shaped body, I have body reference coordinate system. Now, if the potato-shaped body decided to go up, body reference coordinate system will follow the body. It's always attached to this particular location. If it goes left, body reference coordinate system will do the same. If the body rotates, body reference coordinate system will do the same. Now, with help of this body reference coordinate system, we can describe all the particles that makes this body. So it happens such the way that we're first going to describe where is the origin of the body reference coordinate system is located with respect to global coordinate axis. Okay? Then we're going to take a rotation of body reference coordinate system into account. Now that will be made by using 2x2 rotation matrix that is orthogonal matrix. meaning that if you're going to form vectors out from the columns of this 2 by 2 matrix, those vectors will be perpendicular with respect to each other. So they will have a 90 degrees angle with respect to each other. And once we have using this descriptive and body reference coordinate system, then we have here vector u bar, and vector u bar can reach every single particle within the boundaries of the body. So this is how the description works. Extremely important. Also, you need to know a little bit of mathematics. So I might ask about, okay, what is that, is this orthogonal, this matrix, is it orthogonal? What the orthogonality means? Then you have to explain that it means that two vectors are perpendicular with respect to each other, which in two-dimensional space is quite understandable. Okay, so that's the first thing. Then description of spatial body, three-dimensional body. So sometimes I use spatial, sometimes 3D, three-dimensional body. Well, not as important as description of body in a planetary case. Is rated as a 3 stars. 3-star hotel it's good, so it makes sense to use this kind of hotels. But if you're busy, you may skip this. Okay, how is the description of spatial body? So we can use this very same procedure, but this time in a spatial case, the dimensions naturally will be different. So vector R will consist of 3 components. This is going to be 3 by 3 rotation matrix, and vector U bar will have a 3 components. We learned one way to describe this 3 by 3 rotation matrix, and that was based on Euler angles. Euler angles are based on successive rotations. Successive rotation means that you doing one rotation after another. That's what it means, successive rotations. Okay, so how it works and what is the most often used sequence of rotation is that we first getting started with the 2 coordinate system that are parallel with respect to each other. And then I'm introduced into rotation around the z coordinate axis. And amount of rotation is this which I'm not sure what it is, phi, c. That doesn't matter what it is called, but this is amount of rotation. Then we have once rotated coordinate system. And this once rotated coordinate system will be rotated again, this time around the rotated x-axis. Amount of rotation is theta. And then we have 2 times rotated coordinate system, which will be rotated one more time, this time 2 times rotated z-coordinate axis. Now, the successive rotations mathematically can be accounted by multiplying these matrices together, and this is how it reads. I'm not sure if there's any really difficult question related to this. I might ask a little bit like concept related to these Euler angles. Okay, description of velocity, 2 stars. So it's getting to be less significant. Description of velocity is quite straightforward because you get it by differentiating the position equation, this one that we are very much familiar with, once with respect to time. And you get 2 components, translational velocity and angular velocity. Once you differentiate the velocity one more time with respect to time, you will get acceleration, 2 stars. Not so important. And this acceleration consists of 3 components: translational acceleration, normal acceleration, and tangential acceleration. Those are the components. But again, if I would be busy, I would skip this subject matter. Generalized coordinates. This is what I would not skip. I would not skip if I would be you. I would be putting quite a bit of effort to this. And this is easy topic because generalized coordinates essentially means what are the variables in the kinematics we're using, and we're using this kinematic equation. Variables are components of vector R. These components are Rx and Ry, and the rotation, which is theta here. With the u bar is constant because particles cannot move with respect to body reference coordinate system. They both are attached to body because we are dealing with rigid bodies. How many generalized coordinates you need? Well, that depends how many bodies you are dealing with, because every body needs 3 generalized coordinates. So if you have a system with 3 bodies, you need 9 generalized coordinates, and so on and so forth. In 3-dimensional space, it's 6 multiplied by number of bodies. All right, so moving forward, constraint equations. Equally important than generalized coordinates. At least you need to understand the concept, and you need to be able to compute the number of degrees of freedom. This is necessary, and you need to understand the concept. Okay, what it means if the number of degrees of freedom is more than 0. It means that system is dynamically driven, so there's a dynamic system. If it is equal to 1, so this is kinematic systems, which can be solved by using kinematics only. And if it is less than 0, I think, did I say here incorrectly? I mean, of course, if the degrees of freedom is equal to 0, then it's kinematically driven. And if the degrees of freedom is less than 0, then this is our constraint system. And redundant system is that we're constraining the same generalized coordinates. Take a look at the recordings in that regard. This is quite important. Also, make sure that if I give you simple mechanical structure, like just hypothetically something like this, and then this is constrained, let's say that there's a primitive zone here. Make sure you're able to create the constraint equation for any kind of simple planar system that consists of max of 2 bodies. Make sure you understand the concept. And make sure that you understand that the joints are not necessarily in the end or beam-like bodies, but they could be located anywhere you want. Okay, moving on. Oh my God, Jacobian Matrix. Look at the number of stars. I don't even know how if I can count this far. So there are so many stars. Oof, definitely needed. Okay, so let me release you something. In a question bank, there is a different kind of mechanism, and then we're asking from this different mechanism each one of the question that each one of you have to answer, and that is, please compute the Jacobian matrix for the mechanism zone. And how it goes is that there are different options, and you have to select the right out from the different options. And the one thing that you need to make sure that once you see the mechanism, make sure that you understand what are the dimensions, because this is the first simple thing to understand, or to eliminate the incorrect answers. And then most probably you need to either do this all the computing by yourself, or you need to use a symbolic math tool to do so. By the way, regarding to math tool or symbolic math tools, Sura's provided to give you extra video in that regard. I don't know if it is already available, but it's coming. By the way, I kind of like the discussion we have in the chat window. So you guys are wondering if this is a Omena hotel. I don't know. Could be. So a business class, but we have so many stars that, this is unbelievable. For sure, make sure you understand this. Okay, I need to catch up a little bit. So a little bit left behind. So kinematics, 4 stars. Remember that you have to understand this iterative process that is needed to solve the position level, and then the velocity level is just a matter of substitution, as is the case in acceleration level. So this is a procedure of kinematics. Make sure that you understand what kind of system can be solved by using kinematics. That's easy. That is a system where the number of degrees of freedom is equal to 0. Okay? Then moving along, generalized forces. Okay, this is a difficult thing, but try to keep in mind what is our overall objective here. Overall objective is to express all the forces in terms of generalized coordinates. Generalized coordinates, that is a key for the success. Typically, if the generalized coordinates is expressed like t, typically the forces are expressed by using global coordinates. So you need to find a mapping between the global and generalized coordinates. And that you can do by following the principle of virtual work and principle of virtual displacement more specifically. And once you're following that, you will get this relation where there's a delta r. This r is expressed in global coordinates, and delta q. These are my generalized coordinates. And the mapping that is doing the magic for us, converting or mapping from one coordinate system, which is global, to generalized, is this matrix here, which you can get by using partial operation. That's it. Then, another painful subject matter is that you can do the same for inertia forces. Inertia forces can be expressed like this one here. So these are the inertia forces, and now you simply using the same concept here. Excuse me, the inertia forces is simply this one. You're using the same concept that we did for external applied forces, and then you can get the mass multiplied by acceleration and quadratic velocity vector. Mass matrix consists of three components, which is the one associated to translation, one associated to rotation, and one that couples the rotation and translation. This one here is typically equal to 0, and it is equal to 0 if the body reference coordinate system is located in the center of the mass. Quadratic velocity vector, 2 stars only. Not so important. So this is the only this is non-zero if the body reference coordinate system is located outside of the center of the mass. And this is kind of how the body reference coordinate system experiencing rotation, and that's kind of the physical interpretation of quadratic velocity vector. Approaching the end. Augmented formulation, 5 stars. Oh my god, this is a lot. Here, I would like you to understand the concept. What are the unknowns? What is it you're solving? This is unknowns, and how the constraints are introduced there, the equation of motion, that is with help of Lagrange multipliers. So you're adding the constraints to the original equation. That's what the concept is about. Now, with that, let's move on to last in-class quizzes of the day. But prior to that, let's look at a few examples how the equation look like. These are the screenshots from the last year exam. So there are 2 attempts. And this is how they will be available, and how they will be closed. Time to do the exam was 2 hours. We will modify this year to be 3 hours, because I got the complaints that 2 hours may not be long enough, because you want to check and double check that your answers are correct. And yeah, that's highly recommended. So the time limit will be 3 hours per attempt. 3 hours per attempt. Grading method, highest will account. Definitely, you should make 2 attempts. I mean that if you make a first attempt and you're scoring 5 out of 5, you should stop, because it makes no sense to proceed from that. But if you're scoring lower than that, you should make another attempt. The instructions are as follows, where this is a little bit of small font, but it's explaining a little bit about how is an exam. Exam is not yet made, so we don't know how many exam questions we're going to have and how many points in total. But we're going to make it such the way that you will immediately see how well you're scoring once you're done with your exam. And then if you have technical difficulties, you may email to me or Suraj. Email to Suraj, because Suraj knows the exam technology, the details better than I do. Okay? it is mentioned that Suraj is not available 24/7, but from 8 to 5, 8 a.m. to 5 p.m. Okay. Here's an example how the exam, this is actually took directly from the question bank. Okay, so this is not easy. This is a mathematical question. And we don't have that many mathematical questions, but this is an example of what you could face. Okay, let me say how it reads, and let me put the Socrates on. Okay, so the next one is here. So if A is an orthogonal matrix, then A transpose multiplied by A or A multiplied by A transpose is identity matrix. However, it is not necessary that the vectors made from the columns of the matrix will be perpendicular with respect to each other. It is not necessary that vectors are perpendicular. True or false? True or false? And answering the material that you were asking about, the 27th or something, the material that I was showing to you was last year exam. This year exam, we haven't made it yet, so the dates will be updated and times will be updated. Information will be available in the Moodle database later this week. Okay, but now the in-class quiz is on, and so we have two choices, true or false. Now, statistically, we should get at least 50% success rate, and I think it is going to be significantly higher than that. But how much higher than that? Let me hear that. So what is your? Go ahead and enter your answer to Socrates. And again, if A is an orthogonal matrix, if it is orthogonal matrix, is it then necessary that the columns made of the matrix are perpendicular with respect to each other? True or false? Okay, let me take a look. Okay, so there is quite a bit of students that are still thinking this. Then I have two more in-class quizzes. Okay. My guess here today is 82. 82. Let me see what the others are guessing. Okay, we'll see. Oh yeah, somebody else is saying 82 as well. Okay. 25 students are not yet entered the answer. Okay, let me show this to you. Maybe it's more clear this way. Okay, so there's a lot of guesses. No one is guessing 100%, which is a big disappointment. Oh, there is just when I say that there's 100%. Okay, so we're missing 12 students. So momentarily we are good to go. Okay, and one more thing that I need to do today is that I need to send you a Teams invitation for question and answer session that will be right after today's lecture. I forgot to do it, so that will be available momentarily once I'm closing today's streaming. Okay, 6 students are still thinking, so soon we're ready to look at how is the result out from this in-class quiz. So 5 students. And okay, so the 5 last students are still thinking, and while they are doing the thinking, let me release you how is my second in-class quiz. So this is this classic one, how you can describe a particle rotation. Okay, so let's get back to that in a second. But before that, let's take a look how is a success rate in this game here. So the two students are not yet done. So one student is not yet done. So let me close this in 5, 4, 3. I'm gonna simply close this. Okay, 80. Okay, do we have a winner? Yeah, we have a winner. So we have a winner in this lottery. Let me just make a note to myself. We have at least one winner. Do we have another winner? Where is my mouse now? Here. Yeah, we have two winners. Okay, let me see if I have even more than that. Okay, two winners. Very nice. So 90%. So yeah, false. If it is orthogonal, it means that it's perpendicular. That's what it means. Okay. Then the next one, the classic one. How is that you can describe the particle rotation? First option is that you do not describe the particle rotation because it's not making any sense. Then the options are with help of rotation matrix, with help of R, with help of generalized coordinates. Not easy, but doable. Doable, particularly doable if you have followed my discussion. I'm also thinking this is it. So if this would be 100%, I think that I will close today's lecture like that. I will go and celebrate outside. I will using this moonwalking for 2 days roll. 2 days roll. Okay. I will make my wiener dance here. But is it 100% or is it something else? Okay. So 18 students are thinking, 16 students are not yet given the answer, 13 now, 12. Okay. So there's an idea that if somebody's failing, then we should release the information to all of you, so then you can be mad to that one single student. Or if it is not, maybe it's not one, but it could be more than one. Okay. Think about it. This will be outstanding closing because, if we can, this would be 100%. That would mean that you definitely have the can-do attitude for the written exam. Definitely. Okay. So we have all the answers. My hands are shaking a little bit, so I'm a little scared to click this, but I guess that I will do it. So is it 100 or not? Okay, so we have a good news and bad news. Bad news is that it's not 100%. So it's 95%. Good news is that it's very high number. It's not 100%, but it's very good. It's very good. So I want to see how are the chat comments. No way. So you don't believe that by yourself. I have a hard time to believe it by myself as well. So final Inclass quiz, and then I will do this attempt to explain the multi-body system dynamics to you in 10 minutes. Or was it 15? So this is not easy. Then my last question is, what is a physical interpretation of Lagrange multipliers? This is exactly what you can find in exam. So this is a typical example you can find in exam. I'm asking you, what is the physical interpretation of Lagrange multipliers? Force is due to inertia, acceleration of generalized coordinates, rotation of particle. Okay, rotation of particle. Okay, no comments in that. I cannot make any comments. I'm just too confused. And then reaction force is due to the constraint. So those are the four choices, and select the one that is correct. Okay. And now while you're entering your answer, I will We're gonna follow your that comments, which is very nice to follow that. Okay. But you are arguing that this is intentionally. Somebody answered incorrectly intentionally, but I don't think it was the case because it was more than a one incorrect answer. I think it was a total of 3 incorrect answers. So I don't think that's intentional thing. It was just a mistake. Okay, but back to this. So the last in-class quiz for today is physical interpretation of Lagrange multipliers. So go ahead and enter your answer. Okay, so it's quite many students that are still thinking about that. So maybe you guys are okay. Yeah. So again, somebody's proposing that rotational particle would be a safe choice. Safe choice. Okay. Right. So with that, I'm gonna move on to this attempt to summarize story of multibody dynamics within 10 minutes. It's gonna be less than 10 minutes. Okay. I will let you then. I will let you then enter your answer to this last in-class quiz of the day. And then I'm going to shortly explain what is the deal with the multibody system dynamics. I'm not going to follow the comments any longer. I'm going to focus on this. In multibody system dynamics, the only decision, and let me repeat, only decision you need to make is that you need to make an agreement. How is that you're describing particles with respect to your global coordinate system? We make a decision that we're going to use the body reference coordinate system. And once you make a decision that you're using body reference coordinate system, then your kinematics is based on this equation. This equation we have translation of body reference coordinate system, orientation, rotation of the body reference coordinate system with respect to global coordinate system and vector u-bar. That's pretty much all you need to make an agreement with. And once you have this agreement, then you just following the certain procedures very mechanically, no thinking. The first procedure that you have to follow, that you have to be able to express the constraints. These are the motion limitation imposed by using this particular equation. In this equation, which express the point with respect to global coordinate axis, you're saying some limitation to this point. You may say that this point have to be common with 2 bodies, or it have to be the point where you attach this to ground by a revolute joint, or whatever you want. This is going to be your constraint equations. Now, in this kinematic expression, it's extremely important to understand what are the variables, what are the numerical values that are changing when the body is translating and rotating. Those ones are called generalized coordinates. And if you have one body, you have 3 generalized coordinates like shown here. If you have more, then it's going to be 3 multiplied by number of bodies. Once you know the generalized coordinates and once you know the constraint, then you can solve the Jacobian matrix, which is very fundamental when you're solving dynamics and kinematics. Now, moving forward, then you are in multibody system dynamics, you are expressing your forces using these generalized coordinates. And this you can make it happen with help of virtual work, virtual displacement to be more specific. And in virtual displacement, you find the relation between R and Q. This is global coordinates, this is generalized coordinates, and the relation is this matrix here, which writing that with a better font is partial R, partial Q. This is your mapping matrix that converts externally applied forces and inertial forces to be expressed by using generalized coordinates. These ones that are telling you how is a system configuration at any given time. And then once you're following the concept of virtual work, you're adding your constraint to your equation of motion by using Lagrange multipliers. Then you can set this equation to be equal to 0. And once you take additional information in a form of constraint equations into account, this is what tells how is your system behavior. So this is called set of differential algebraic equation, and that can be converted to be ordinary differential equation by differentiating the constraint twice with respect to time. That's it. Look at that. Faster than 10 minutes. Within 6 minutes, the multi-body system dynamics. And with that, we're going to move on to last in class quiz. My personal prediction in success rate here is 63, 64, 60, 66, 66. That's what I'm guessing. Okay, so I mentioned the solution for this in-class quiz already, I think, like 5 times during today's lecture, but maybe it's not that easy to recognize it. Okay, so we have all the students here. So the success rate is 74. It's okay. It's quite good. And good news definitely is this. I need to go back to this one here. Good news is this. No one, let me repeat it, no one voted this one here, rotational particle. But somebody voted to forces due to the inertia, which is not correct. Acceleration of generalized corners, which is not correct. So the correct answer is reaction forces due to the constraints. And with that, I promise that I'm going to close early today. That's exactly what I'm planning to do because I've been online already hour and 25 minutes, so it's supposed to be hour and 30 minutes. So I'm closing, 4 minutes before the deadline. So what happens next is that you will get the calendar invitation for team session that will come after 2 minutes, and you can join to Teams by simply clicking the icon, and then we can discuss more about the practical matters related to exam. We can discuss about rotational particle if you may, or whatever you want. So with that, see you in 2 minutes in team session. Bye now. And how can I close it here?